Let me throw that back up here for a quick second. All right, so we do get that. Critical numbers, of course, there's just how many? What's the critical numbers? 1. It makes it undefined. There's no way to make it 0 because the top is always 36. I like it. So sign diagram, throw 1 in there. It's undefined at 1. Yes, ma'am.
What was the way that you figured out that you showed the second derivative? Oh, you actually did all the work. I thought you did some shortcut.
No. Yeah. Nope. If there was a shortcut to that, you better damn well believe I'd do it. Yeah. You just got to do all the work. Too bad for all of us. Okay. And then if I throw in there, see, the bottom is got odd multiplicity, so it's going to change signs. So if I put in there a positive thing, it's positive, put in a negative thing, it's negative. I like it. So down here it is concave down. Up here is concave up. So the inflection point is interesting. I like it. The inflection point is actually the vertical asymptote. So it kind of makes sense. If I have a vertical asymptote, things can completely change on the other side. That's why critical numbers also come from where things are undefined. So look here. What did the concavity do from one side to the other? It changed. Well, it's a concavity right here. Doesn't exist. Maybe. All right, let's see. So find intercepts. Plot and label asymptotes. So what asymptotes do I have? We know what the vertical asymptote is from the beginning. What's the vertical asymptote? X equals 1. What's the horizontal asymptote for this one? This one, oh, you guys are really going to love me. What situation am I in? Remember the 3 situations. I can't remember if this has come up before. Yeah, the 3 situations. So the top degree is higher than the bottom. Do I have a horizontal asymptote? When X gets really, really, really big, is the bottom able to keep up with the top? Nope. So the whole thing goes to infinity, but it's not a horizontal asymptote. It's a funky ass asymptote, right? Which, I don't know what you guys called it. There's 2 different names for it. The standard one is slant asymptote. If you had an all fancy schmancy teacher, they call it an oblique asymptote, right? Slant kind of makes sense because it's slanted. Anybody remember at all how the shit to find that? Slant or oblique asymptote. Yes. Divide, long divide. Or synthetic division, right? Which way do you want to do it? You know, if you don't know synthetic, you obviously don't want to do it that way, but I hope to God you all know synthetic division. So synthetic, I put 1 in the penalty box. 2, 16, 0. That's all my coefficients. Bring the 2 down. 2 times 1 is 2. Add, multiply, add. It was x squared, so now this is going to be the coefficients of x, the 1s, and then the remainder. So the slant asymptote is this line, because what happens to this piece when x gets really big? This piece goes to 0. Oh, shit. Deep dive into the past. So the slant asymptote is the equation 2x plus 18. What about intercepts? Take a minute to figure out the intercepts. Now, of course, I'm using the original function for this. So what do you guys get? X-intercepts, you got 0 and -8. And of course that makes the y-intercept have to be 0, 0. Okay, so anybody tell me, look at the x-axis. What scale should I maybe use on the x-axis? Up here, if I look at my min and max, they go -2 and 4 for x values, but then I have an x-intercept at -8. So maybe make a scale of what? Each tick mark, make it what? 2. I like it. Go by 2s. That's beautiful. This is exactly what I would do. Could you go by 3s if you wanted to? Shit, yeah. Go by 1s? Not with what I gave you. Now, if you bring your own graph paper, you got a little bit more flexibility, but I will give you a little graph thing. What about the y-axis? This is where it's going to get interesting. Look at all my y values for my important points. Yeah, beautiful. I'm going to go by 8s. I mean, those kind of land right on multiples of 8. Shit, yeah. So, 16. Plus, where was it, Jeff? You could do it. There was something else. No, I guess it's just the 32. You want to look past 32 a bit, so this is going to end up getting me up to 40. And then down here, I've got negative. So let's put in there my vertical asymptote. Little vertical. My slant asymptote. This is going to be a little interesting with our scale. But let's see now. If I put a -2 into this, I get -4 plus 18 is 14. Let's see if you guys are cool with this. And if I put a 2 in, I get 4 plus 18 is 22. And of course, if I put a 0 in, I get 18. No idea if you guys are following me here. So I'm trying to get what my slant asymptote looks like, roughly. I could be a little more specific about x-intercept. That looks about right. The x-intercept should be -9, and it looks about -9. Oh my God. I'm easily excited. Any way you want to graph this thing using the scale you created, you need to put that wall in there. Okay, okay. What do I put next? We kind of work backwards normally. I put my intercepts, 0, 0. And -8, 0. I like it. Inflection point, it's really not. It's it's the asymptote going to be where it changes. So I don't really have an inflection point to worry about. So what do I start off as? I start off going. Up with concavity down. So I want to go up like this way, right? Concave down. How do I go up, concave up? Like that. So this is up, concave down. This is up, concave up. I like it. So if this is unemployment, this is a good thing. It's increasing, but it's increasing at less rate. Unemployment, this is a bad thing. It's increasing and just keeps going up fast. Oh, shit. Okay. So I'm going to go up with a down. And I don't have... Where am I at? Oh, I haven't put my maxes on there yet. So there's a max at -2, 8. And let me put there max. And there's a min at 432. And now we see why that makes sense. Okay. So another thing that a vertical asymptote could do to you is you have to kind of restart after it. So I'll show you what I mean. So I know I'm going up, concavity down, so I know I'm going like this. Wee-ah! Hit my max, and then come back down through this. And then what's going to happen over here? So concave down, there's my maximum. And what's going to happen over here? Approach that wall. I like it. Then I have to restart over here. So after 1, what am I doing? I've got concave up, and I'm decreasing. So that means I'm coming, and this kind of makes sense. Concave up, decreasing, hit my minimum, and then I kind of want to follow this guy. That is so yummy. So again, if I just want to check it real quick, we put in here 2x squared plus 16x divided by x minus 1. Okay. And then let's make my window the same. I go from -10 to 10, and I go from -40 to 40. Let's see if we are completely wrong, or what's up. Ooh, that looks nice. Now, I'm going to put one more thing in here. Let me put in here 2x plus 18. There's my slant asymptote. See that? That's bodazim. I like it. Just to make a new word. Yes?
You go back up to the max. Okay, and can you go down to the inflection points? So when you got to that point, what am I looking for there for the inflection point?
So where is the concavity changing? What x value does it change? 1. What's wrong with 1, though, when I try to plug it back in to see what the point is?
It's undefined.
Yeah, 1 is the location of a vertical asymptote.
So that should be my note that at that point I should realize, oh, that's a vertical asymptote.
Yes, and that is another place. Vertical asymptote can reset the function entirely. So it could be concave down on one side and up on the other side, which is, again, why critical numbers come from not only where the stuff is 0, but also where it's undefined. Vertical asymptote is somewhere where things could change. Okay, I like it. I like it. You guys, let's change topic. We'll do this one next time, but I want to. We've been doing enough of these, I think. You guys agree with me or no? You want to do another one? It's up to you guys. We could do this and do the other stuff I was going to do later. You want to change a topic for a minute, like get a cracker in there before you try the next type of wine. And you're like, Jeff, this is not wine. Yes?
So when it comes down to figuring out the asymptotes, we know that there's one at 1, and then you're saying that we should be looking at the original problem, going back to our pre-calc in terms of how to find asymptotes.
Oh, hell yeah. Big time. I like it. I like it. And in 4.5, I can't remember if they put a little review in here. Yeah, page 316, they talk about horizontal and vertical asymptotes and slant asymptotes.
Okay, so
Yeah.
4 or 5.
Yep. So they have a little bit of review in there. I like it. Anything else? Any opinions? I'm going to just make my decision and say we'll do this one next time. I want to talk about a different topic. I might as well stay up here on the overhead. Shoot, what was it? There was one thing left over. Before I do this, what was it, Jeff? Oh yeah, that's right. Beautiful. So, 2 things I want to talk about, and there's plenty of time. One thing is very quick and easy. If I say first derivative test, what does that relate to? Where's that on the work we did? That's when we make a what and first derivative test. Yes, so I make the sign diagram and I do all that kind of business, right? And I don't know if you guys remember, I said real quick earlier, sometimes there's a method that will shortcut that. So there's something called the second derivative test. The concept is just so frickin' straightforward, it's insane. If I have a critical number at x equal to a, and I know that the second derivative at a is greater than 0. Now, what does that mean? What I just wrote down. What does this mean is happening through a? What's the second derivative tell us? First derivative tells us slope. Second derivative tells us concavity. So I know it's concave up. Can everybody make a concave up shape with their hand? Yes, there's concave up. If there's a critical number in a region that's concave up, what is that the location of? So if I have a concave up and there's a critical number at that where it's concave up, that is the location of a minimum. That is the second derivative test. So let's go back. Let's see. Let's look back at one we've already done real quick. Maybe one that's not too crazy. Shoot, where's my other one? There you are. No. Here we go. So that very first one we did, and I've already thrown away. Here you are. All right. This one, right? The very first one we did. Let's reanalyze these real quick. Stay with me now. So let me write down what we need from this. So I know that the critical numbers were 0, 1, negative 1. I know the second derivative was 30x times 1 minus 2x squared. What is f double prime? Let's go backwards here. What's f double prime of negative 1? Is it positive or negative? That's really all I care about. If I plug a negative 1 in here, what do I get? I get a negative times a negative. So I get a positive. That's greater than 0. So if it's greater than 0, that means it's cup up. So what's true at negative 1? There must be a... If it's cup up, there must be a minimum. And sure enough, we got a minimum. All right, what about 1? What's in concavity 1? I get positive times negative is less than 0. There must be a max, and we got a max at 1. So now here's the reason why we have first derivative test and second derivative test. What is f double prime of 0? 0. So it's inconclusive. I'd have to go back and do the first derivative test at least for 0 because the second derivative test doesn't tell me. So if the second derivative is 0, that means the second derivative test can't tell what's going on there. You have to go back to the first derivative test. When else is the second derivative test gross if the second derivative is gross, right? So there's like give and take for both. That's why they both kind of exist. Okay, maybe. So if they ask you to use second derivative test to figure out what the local maxes and mins are, don't go, shit, what does second derivative have to do with max and min? Well, this is what it has to do with max and min. The shape through that point will tell me if it's a min or a max. Now, you've got to be really, really careful. If I have a function, I'm not even going to tell you what the function is. And I know that f double prime of 3 is greater than 0. Does that mean that's the location of a minimum? No, I don't know. Because what's true about the concavity, every point on this thing, it's positive, right? It's concave up. So what was it about this that made me know it was a min or a max is that I was only checking the critical numbers. Because that's the only place that maxes and mins. So those two together, it's a critical number, so that's where max or min could happen. Look at the concavity, helps you determine which one it is. Okay, maybe. So that second derivative test, it's a beautiful idea. And sometimes it's really great when the second derivative is easy. Okay. The next idea, and the last idea for today,